Hello everybody, my name is Bo Li. In this video, I will present a paper called On the Effectiveness of Partial Variance Reduction in Federated Learning with Heterogeneous Data. This work is a collaboration with Mikko Schmidt, Tommy Alstrom, and Sebastian Stich. So in this paper, we proposed a partial variance reduced algorithm FedPAR for dealing with data heterogeneity in federated learning. We then theoretically prove that our algorithm can converge as fast as centralized SGD in most practical relevant cases. Furthermore, we experimentally demonstrate that our algorithm is more communicationally efficient than the baselines. And we also show the diversity between the feature extraction layers and alignment between the classifiers are crucial for the success of our algorithm. Next, I will give a detailed explanation of this paper. So I will first talk about the federated learning problem setup. Federated learning usually consists of a server and clients. A server can be, for example, a data center, and each client can either be a mobile device or large organizations such as hospital. And each client will have some data that's available to use. And in each communication round, the server will distribute a model to the participating clients. Then each client will update the model with its own dataset for multiple steps. When this is done, the client will communicate the updated model parameters back to the server for aggregation and finishing one round of communication. To formalize this scenario, we can formulate our problem as minimizing the average of the loss function across multiple clients. We can define the loss function as the expectation of the loss with respect to the stochastic sample from the distribution on a single client. However, in federated learning, since each client collects the data individually, it's unavoidable to have heterogeneous data distribution. Therefore, addressing the issue of data heterogeneity is very crucial in federated learning. To do so, we first revisit a federated averaging algorithm, which is a popular algorithm in federated learning. We want to understand what is the main reason for the unsatisfactory performance when the clients are heterogeneous. We performed a simple experiment with using VGG11. We use CVPR10 dataset, and we split the data following Dirichlet distribution using concentration parameter alpha. When alpha is small, the clients are more heterogeneous. We then define a quantity called drift diversity that can indicate the agreement between the model updates across clients. And here is the result. We see that when the early layers in the over-parameterized neural networks have higher agreement because no matter how heterogeneous the clients are, the drift diversity are very similar. However, the story is different when we go deeper in the neural network. Especially for the classifier, we see that the drift diversity for the experiment where the data heterogeneity is high is much higher than the experiments where the data heterogeneity is low. And these observations agree with some of the recent literatures. To address the issue of data heterogeneity, many works have been proposed, and the scaffold is one of the popular approaches that applies variance reduction for the entire model. However, its performance in deep neural networks have not been well explored, and it can be a communication bottleneck for some of the low-power edge devices. And since here we have observed that classifier is the main reason for the client drift when the clients are heterogeneous, in this paper we propose to apply variance reduction only on the classifier. We formulate our algorithm as below. So we first define a vector that contains either 0 or 1. Then on each client, for the set of indices where the corresponding values in P are 0, for example, feature extraction layers, we perform standard SGD updates. Then for the set of indices where the corresponding value in P are 1, for example, classifiers, we perform variance reduced update with using control variate C. And we repeat this process for k steps. Then we update the control variate following this equation. It's worth to notice that our control variate has a size of V, whereas in scaffold, control variate has a size of D. And in most neural networks, V is much smaller than D, which means that we only need to transmit much fewer number of parameters between the client and the server. When this is done, on the server side, we perform the standard model aggregation and control variable aggregation. When p is 0, we recover federated averaging, and when p is 1, we recover scaffold. We repeat this process for R runs. Here is a simple illustration of classifier variance-reduced architecture. And next, I will talk about the convergence rate on strongly convex function. For non-convex function, please have a look at our paper. For our theoretical result, we assume zeta heterogeneity, where zeta measures the function dissimilarity. And we also assume the variance of the stochastic noise is bounded by sigma square. So compared to the result in scaffold, we see that when p equal to 1, we can recover the convergence rate in scaffold as by definition zeta square 1 minus p equals to 0. Then we see if the second term is sufficiently smaller than the first term such that the first term is dominating the convergence, then we can match SGD with mini batch size of k on each worker. To illustrate the effectiveness of our proposed algorithm, we perform experiments on different datasets, multiple neural networks, and different levels of data heterogeneity. Here we show the required number of rounds to reach the target accuracy. Compared to the baseline approaches, we see that we require fewer number of rounds to reach the same level of accuracy. We also report the top 1 accuracy, and we see that for some of the experiments, our performance is even slightly better than the centralized experiments. And this result demonstrated the effectiveness of our proposed algorithm. So to summarize, in this paper, we proposed a partial variance reduced algorithm fedPAR for dealing with data heterogeneity in federated learning. We then derived convergence rate and discussed some of the special cases. And finally, we experimentally demonstrated that our algorithm can reduce communication cost and improve the top 1 accuracy.